Hello, this is Sergio Cicero from University of Cantabria, and I'm going to present this work entitled Some Thoughts about the Application of the Master Curve Methodology to Ferritic Steels Containing Notches, a work that has been done in collaboration with my colleague Sergio Arrieta. The contents of the presentation start with an introduction to the topic covered by the work, then a brief overview of the master curve as an engineering tool to assess ferritic steels containing crack-like defects. The third section will be focused on the use of the proper master curve in notched conditions instead of cracked conditions. And finally, a couple of conclusions summarizing the work. Here you have some experimental results obtained by Wallin and published in 1998, where you can see the fracture toughness results along the ductile to brittle transition zone of a given steel. At lower temperatures, we will have the lower shelf with cleavage fracture with multiple initiation points. And at higher temperatures, we will have ductile fracture mechanisms. And in between, we have the proper ductile to brittle transition zone. Here we may observe two main things. The first one is an evolution of the fracture toughness with temperature. By increasing the temperature, we obtain higher values of the fracture toughness. And also we may see that for a particular temperature, the fracture toughness results have a great amount of scatter. So statistics must have a key role on these processes of fracture. Together with the experimental results, you may see here these curves, which are the proper master curve. That is the assessment tool developed by Wallin that provides estimation of the fracture toughness of the material along the ductile to brittle transition zone. And of course, this is addressed for crack-like defects specifically. However, we may have defects that are not crack-like, but we may have notch type defects, on which the main difference is that we have here on the tip a finite radius, reducing or generating less demanding stress fields here on the tip. As a consequence, the apparent fracture toughness developed by the material in notched conditions is higher than the fracture toughness obtained in cracked conditions, and this of course affects the fracture resistant values obtained along the ductile to brittle transition zone. So what we want to do in this work is to see whether or not the different hypotheses sustaining or the different assumptions sustaining the use of the master curve in cracked conditions, to see whether or not they may be applied to notched conditions as well, and to provide experimental results validating the use of the master curve in notched conditions. So, what is the master curve? Going back to the fracture toughness results shown previously, along the ductile to brittle transition zone, cleavage fracture occurs generally from a single initiation point, and there may be also some previous limited ductile tearing. There are a number of cleavage promoting particles, but there is just one that is the triggering particle, let's say. So at the end is a process that follows weakest link statistics, and weakest link statistics may be statistically analyzed through a 3-parameter Weibull distribution, and the cumulative failure probability in such distribution follows the expression that you may see here, where the two weighable parameters are k-mean, the location parameter, k0, which is the scale parameter, and b, which is the shape parameter. B being the thickness of the specimen being tested, and b0 being the reference thickness. So for a given material, we should define b, k-mean, and k0. The assumptions made by the master curve are therefore that the process follows weakest link statistics and that it may be modeled with a Weibull distribution with these three parameters. But additionally, B is 4 as demonstrated by Wallin based on experimental results. K-mean is 20 megapascals meter to the square. K-mean at the end is the value of the stress intensity factor below which cleavage is not possible. So it is a threshold value. You need this 20 megapascals meter to the square to generate cleavage. This has also been studied by and demonstrated by Wallin from experimental results. K0, the scale parameter, follows this expression, and this is an experimental fitting equation. It was obtained by fitting a number of experimental results, and Wallin demonstrated that K0, the scale parameter, depends on a material parameter known as the reference temperature, which is the temperature at which the median value of the fracture toughness is equal to 100 megapascals meter to the square. And also, the master curve methodology establishes a censoring criterion, ensuring that small scale yielding conditions and high constraint conditions are fulfilled. If all these assumptions are fine, and as it has been demonstrated by Wallin and co-authors, then the expression for the fracture toughness is this one here for a given probability of failure. So for a 95, 50, and 5% probability of failure, the corresponding equations are these ones, which are the curves that we had seen in the previous slides. So we published 5 or 6 years ago the direct application of the master curve on notched conditions, and we obtained rather good results in steels 275 and 355. And we applied the master curve directly, assuming that the different hypotheses sustained in the master curve were correct, but without going into the details. In this work, we provide validation on more materials. In this case, we add steel 460 and 690, and we discuss about whether or not the hypotheses sustaining the master curve in cracked conditions are valid in notched conditions as well. So, concerning the two first assumptions, when we have for a given material and notch radius a given ductile to brittle transition zone, within that zone, the failure is also caused by cleavage. And also, it starts from a single initiation point generally. So it follows weakest link statistics, and then it may be modeled by a 3-parameter Weibull distribution. So this is exactly the same as it happens in cracks. No problem about that. Then, concerning the shape parameter, in cracks, it takes the value of 4. To check the value of this parameter on notched conditions, we have a number of sets of experimental results combining a given material with a given temperature and a given notch radius. You may find it in the references and in the literature. And here you have some results. You just have to rank for a given set. You have to rank the different results and represent them as you may see in this figure, obtaining the corresponding slopes. We made this for all the available sets developed within our laboratory and obtained something like this. This is the well-boosted slope B, and this is the number of tests for each set of tests, and these are the confidence margins that were represented in the same way that Walling did for cracked specimens. You may see that the assumption that B is 4, which is this horizontal line, is quite reasonable because most of the points lies within the confidence bands of 5 and 95%. So it looks like B equal to 4 in notched conditions is also an appropriate result. Concerning the minimum value of K to obtain cleavage fracture, provided it is the same fracture micromechanism, we are going to assume that this value is also valid for notches, because if you need 20 megapascals meter to the square for a cleavage fracture to occur in cracked conditions, you will need at least the same value in notched conditions, if not additional amounts of stress intensity factor. But in any case, considering 20 is a conservative assumption. So, in principle, we may take this minimum value of K. Another one, K0. As I mentioned previously, K0 was obtained by fitting a number of experimental results, and this best fitting provided this curve. If we represent our experimental results in notched specimens, we may see that, well, they fit rather reasonably to the fitting curve. Of course, we will need more experimental sets, and probably the curve will change a little bit for notches, but it looks reasonable to use this same expression for notches as well. And finally, concerning the censoring criterion, it is something similar to K-mean, considering the same expression for notched specimens will be in any case somehow conservative, a conservative assumption. So we may use the same expressions for notches. With all these, and once the different hypotheses have been analyzed and accepted, the expressions of the master curve for notched conditions will be like these ones, which are exactly analogous to the expressions in notched conditions, but using here the apparent fracture toughness, which would be the apparent fracture toughness, the apparent reference temperature, which would be the temperature at which the average value, the mean value of the apparent fracture toughness is equal to 100 megapascals meter to the square, and which is obtained in exactly the same way as the reference temperature in cracked conditions is obtained. Now, if we represent all of our experimental results with 4 steels, different notch radius and different temperatures, you may see that the master curve provides accurate results or accurate predictions of the apparent fracture toughness within the ductile to brittle transition zone. Here we have some results for which predictions are conservative, but in any case correspond to tensor results. So even the tensoring criterion works properly here. So Conclusions, just two conclusions. The different assumptions of the master curve may be justified in notched conditions, and the experimental results validate the use of the master curve in notched conditions. That's all. And if you have any questions, it will be a pleasure to try to answer them.